In this video, we're going to talk about an important and actually, in my opinion, really cool theorem that pertains to orbits and stabilizers of group actions. So for this video, we're going to let G, a group, act on X. And you'll recall just a couple of definitions. If X belongs to X, I'm going to try and be really clear with lowercase versus uppercase here, then the stabilizer of X, and I'm going to say stabilizer in G, just so that there's no reason to get confused here. The stabilizer of X is the set of all G in my group, such that G acts on X to produce X. In other words, G leaves X alone. That's the stabilizer, and we know from a previous video that this is a subgroup of G. All right, so there's that. And then I have this other definition, the orbit of X. That is the set of all elements of my set, all elements Y in X, such that there exists a G in the group for which G acts on X to produce Y. Okay, so in other words, the orbit of X is the set of all elements in the set that I can get to by acting on X with a group element. All right, and we did some examples in previous videos, so if you would like more review, go back and check those out. In this video, we're going to prove an important relationship between the size of the stabilizer of an element and the size of that element's orbit. Before we get to that, though, I want to do a little example that sets the stage. So I'm going to pick a different color here. And we're going to have the units mod 15. Remember, that's the multiplicative group of congruence classes mod 15 that are relatively prime to 15. So I'll just put units mod 15 under times. We're going to have that act on the set Z mod 15. And it doesn't matter whether that's under addition or multiplication because it's only being regarded as a set. This is going to be similar to an example that we did previously. We're going to have this act by, let's call the units U. U dot X equals UX in mod 15. And we're going to analyze orbits and stabilizers of various elements of Z mod 15 under this group action. Now, as I was planning this video, I thought, well, we could just do all the arithmetic by hand, and that would be straightforward enough. But then I thought, we got U mod 15 acting on Z mod 15, and there's an awful lot going on there. So let's just pull in a multiplication table. So it turns out that Wolfram Alpha actually lets you do this. You can enter whatever mod you want, and it'll spit out a multiplication table in that mod. So I have right here a multiplication table mod 15. Let's see if I can find it. There it is. So I'm just going to move that over. Hope that that's visible. I know that the numbers are rather small. But anyway, we need to take into account here before we get started that we're talking about U mod 15 acting on Z mod 15. So let's write down what U mod 15 is. U mod 15 is, that's the set of all units mod Z15, or rather group of all units. So relatively prime to 15. 0 is certainly not, 1 is, 2 is, 3 is not because there's a common factor of 3. 4 is, 5 has a common factor of 5, 6 has a common factor of 3. I'm just reading down the left column. 7, 8, 9 has a common factor of 3, 10 has a common factor of 5, 11, 12 has a common factor of 3, 13, 14. There are 8 units mod 15. All right, so that means that we're only going to be focused on certain columns of the table. Or actually, maybe a little bit more faithful to our intent here, since we have U being multiplied by X, would be to have only certain rows of the table highlighted. So I'm going to use my highlighter to highlight a few rows of the table. So only the rows corresponding to units. Let me pull out my yellow color here, highlighter, let's make that nice and thick. Let's have it size 10, that sounds good. Okay, my units are 1, 2, I worry that this is making the numbers fainter, that's a little bit troublesome. 4, 7, 8, 11, 13, and 14. And now we can use this to figure out the orbits and stabilizers of various elements of our set. Those are the ones up here, 0 through 14. All right, so let's take a few examples. Let's start with something that is itself a unit. So let's try the orbit of 4 and the stabilizer of 4. And we're just going to assume at this point that we know that we're talking about orbits and stabilizers under U15, not some other subgroup. All right, so first of all, the orbit of 4, let's just look. If I multiply 4 by units, so I'm not looking at this entire column necessarily, I'm just looking at the products of 4 with units. I've got 4, 8, 1, 13, 2, 14, 7, 11. That appears to be all of the units. Now, because the orbit is a set of set elements, not a group, I'm just going to go ahead and write down all of the units. I'm not going to say it's U mod 15 because I'd be suggesting that the orbit is a group, and it doesn't have to be. 11, 13, 14. And what about the stabilizer of 4? It looks like the element 1 stabilizes 4. That is, 1 acts on 4 to produce 4, but that's it. So the stabilizer of 4 is just the identity subgroup consisting of 1. So that's one example. Okay, what about something else, something not relatively prime to 15? Let's try the orbit and stabilizer of, how about 6? Well, the orbit of 6, that is the set of all things I get by acting on 6 with a unit. So again, remember, just highlighted rows, 6, 12, 9, 12, 3, 6, 3, and 9. Okay, kind of an interesting order there, but it looks like all we're getting is 3, 6, 9, and 12. And by the way, those all share a certain relationship with 15. They are all the numbers whose GCD with 15, well, all the numbers between 0 and 14, whose GCD with 15 is 3. The stabilizer of 6, certainly 1 stabilizes 6, but you'll notice there's something else too. 11 stabilizes 6. So the stabilizer is the subgroup consisting of 1 and 11. And if you don't believe that's a subgroup, well, please refer to my previous video that says stabilizers are subgroups. But if you're wondering whether 11 squared is actually 1, well, check it out. 11 squared is 121, which is congruent to 1 mod 15, because 120 is a multiple of 15. So that's my orbit and stabilizer in that case. What about a multiple of 5? How about the orbit and stabilizer of 10? And I'm just sort of picking ones at random here, although I'm trying to pick them so that they'll be different. So if I look at the 10 column, it looks like the orbit of 10 just consists of 10 and 5. I mean, look, all these 10s and 5s here. I don't seem to get anything else. I do get 0, but not by acting with a unit. So the orbit of 10 is just 5 and 10. What about the stabilizer of 10? Well, the stabilizer of 10 looks like it's 1, and then 4 also stabilizes 10, and then 7 stabilizes 10, and 13 stabilizes 10. How very interesting. Okay, so that appears to be a subgroup of units mod 15. And finally, let's look at something ridiculous. The orbit and stabilizer of 0, because 0 is also a perfectly good element of this set that's getting acted on by the group. The orbit of 0 is just 0. You don't get anywhere else. And the stabilizer of 0 is, now this really is the group U mod 15, but I'll list all the elements anyway. 8, 11, 13, 14. Okay, so so far this is just an expansion of the lovely example that I did in the previous video, but I was happy to have the chance to do it. But now let's see if we can get some insight here. I'm just going to write down next to each of these sets the size of the set, whether orbit or stabilizer. So here I have orbit 8. Orbit has 8 elements, stabilizer has 1 element. Here the orbit has 4 elements and the stabilizer has 2 elements. Here the orbit has 2 elements and the stabilizer has 4 elements. And then here the orbit has 1, the stabilizer has 8. Okay, so we're seeing a pattern. But let's see if we can substantiate in some way. I mean, it looks like we're going to get that the orbit times the stabilizer, so let's say the orbit of x, the size of that times the size of the stabilizer of x, is always 8. Okay, why 8? Well, let's take a closer look at the example with 6. I feel like that's probably the most illustrative of the 4. So if I look at the column for 6, I'm going to go ahead and crosshatch this with my highlighter again. There we go. Beautiful. This is so pretty. If I look at that, then I notice that the orbit has 4 elements, 6, 12, 9, and then down here 3. And each element in the orbit seems to get hit exactly twice. I see 2 3s, 2 6s, 2 9s, and 2 12s. Okay? I claim that this is not a coincidence. This is something that happens for an actual group theoretic reason. Okay, and I'm going to summarize it here, but I'm going to formally prove it in the next video, and then that'll be our last video on the orbit stabilizer theorem. So why does this happen? Well, we know that there are two elements which stabilize 6. Let's just start by taking that as axiomatic. There's two elements which stabilize 6. Given that, suppose I have a group element which maps 6 to, say, 12. So 2 does that. 2 takes 6 to 12. I'm going to write this down over here. So I just notice 2 maps 6 to 12 under this group action. That is the group action dot there. Okay? And I also know that my stabilizer of 6, the thing I started with, was the subgroup 1 and 11. Okay, well, what if I did this? What if I acted on 6 with 11 first, which stabilizes it, and then act on that with the number 2? Okay, so I know because 11 is in my stabilizer that this is going to be 6. And then I'm going to end up with 12 again. Okay, but doing this is really the same thing as acting on 6 with 2 times 11. 2 times 11 in the units mod 15. We don't usually call that 22, by the way. We call that 7, because 7 is the same as 22 mod 15. So it looks like not only should 2 send 6 to 12, so should 7. Is that true? Well, 2 definitely sends 6 to 12. We have the evidence right here. But 7 also sends 6 to 12, as promised. So the idea here is, if I have an element of my orbit, then I can find potentially several elements of the group which send 6, or wherever I'm starting, x, to that particular orbit element. And those are going to be, well, there's going to be one group element which sends x to that element y, but then I can come up with other elements by composing with the stabilizer. Okay, I realize that explanation was just mostly word salad there at the end, but we're going to pin this down and make it much more precise in the following video. So look for Orbit Stabilizer Theorem Part 2.